We are now on the second part of this lecture, which is the hydrostatic force on curved surfaces. So as engineers, we calculate forces on curved surfaces when we are designing components such as tanks, pipes, and curved gates. So this is an example of a curved gate in this figure. So in solving hydrostatic pressure on curved surface, it is easier to translate this resultant force that is acting on this curved surface into its horizontal and vertical components. So it means that we should determine first the horizontal equivalent hydrostatic force acting on this curved surface, as well as the vertical hydrostatic force. So it means we have to find f of x and f of y. So after determining f(x), f of y, we just determine the resultant force acting on that curved surface. Now, to determine the horizontal component of that equivalent force f of x, so we will just apply again the same solution as the plane surface, where we will apply the product of unit weight of the fluid times bar h times a. So since our force here is horizontal, it means that our area that is needed to solve this hydrostatic force is that that area should be perpendicular to that force. So we need to make this curved surface a flat surface that is perpendicular to this horizontal force. So what we will do is that have its equivalent surface that should be perpendicular or flat surface. So this surface right here is just the side elevation of this curved surface. So when we take a look on the left side or on the right side of this curved gate, so what we will see is a rectangular surface. So let's say it has a width. So that's the width here, and this is the total vertical distance, say the depth of this curved surface. So for the horizontal force, so what we need is a flat surface that is the side elevation of this curved surface. Okay, from that we can determine the area as well as bar h, or the distance from the center of gravity to the water surface, and multiply it to the unit weight of the fluid. Then we will be able to determine the horizontal force of the fluid. Okay, for the vertical component of that equivalent force, so let's say we have again a curved gate. We have a solution of Fy equals to the product of unit weight of the fluid and the volume. So this volume right here is the volume above that curved surface. So what we will need to do to determine that volume is that if this is your curved surface, okay, so from the edges of this curved surface, you will just extend vertically, okay, this up to the water surface. So if this is your water surface right here, so this is the left side edge, right side edge, you extend that up to the water surface. So this point right here is already at the water surface, but on this right side of this curved surface, if we will extend that vertically up to the water surface, so the area, and considering that it has its width, so it is a volume, uh, the volume covered by the curved surface above it going to the water surface is your volume required to determine the equivalent vertical force. Okay? So, we have two cases here. Uh, Before we determine the hydrostatic force, uh, for the vertical force, we have two cases here. The first one is the water is above the curved surface. So when we try to extend the both edges of the gate, it is filled with the liquid. On the other hand, on this figure, is that when you extend vertically the points from the edges of the curved surface, so it didn't cover the fluid because your fluid is below the or on the side of this curved surface. So if this is just if this is not filled with fluid, our equivalent vertical force here is going upward. So again, if we were going to compute the f of y, we will still apply unit weight by the volume above the curved surface. So it means the volume that we are still going to use here is the same, this volume right here. Okay, so only that, since the fluid is below and and on the side of this curved surface, so the direction of our hydrostatic force is upward. So unlike in this one, the curved surface above it is filled with the fluid. So means that the hydrostatic force along the vertical is downward. So now, since we already have the equivalent vertical force, so we can now compute the resultant hydrostatic force by computing it by the square root of the sum of the squares of the horizontal and vertical force. So let's solve this problem right here. Surface AB is a circular arc with a radius of 2 meters and a width of 1 meter. The distance AB is 5 meters. The fluid above surface AB is water. Find the magnitude and line of action of the hydrostatic force acting on the surface AB. So we are required to determine the magnitude as well as the line of action of the hydrostatic force. So it means if we are going to determine the equivalent forces that is acting on this curved surface right here, we are also required to locate these forces on this figure. So we will determine where the horizontal equivalent force is located as well as the vertical force. So let's solve this. The first question, we will determine first the magnitude, which is the easier one is the horizontal force. So let's compute that first. So if this is your curved surface and we have a width of 1 meter, so if we will just extend this and we look on the left and right side or the elevation of this side elevation of this curved surface, we can form a rectangle that has a width of 1 meter. So the radius of this is 2 meters. So it means if this is a quarter circle, its height, its depth also is 2 meters. Okay, so for the horizontal, okay, that is E equals to fx or fh It's the same. Gamma bar h times A. So bar h measured from the center of gravity of that flat surface to the water surface. So we have 5 meters here, 1/2 of 2 meters, that's 1 meter. So we will have a total bar h of 6 meters. So 9.81 kilonewtons per cubic meter times 6 meters multiplied by the area. Area is 1 meter by 2 meter. Okay, so the equivalent horizontal force, let's just use FH, is 9.81 times 6 times 2. One times 2. 117.72 kilonewtons. Okay. We can also locate the horizontal force by determining YP. Okay, the location of the center of pressure. So as we recall, the solution on flat surface, YP is bar Y plus IG over A bar Y. So bar Y, since this is vertical surface, so bar Y is just equals to bar H. Okay, bar Y is equals to bar H. So let's determine first the centroidal moment of inertia of this rectangle right here. So BH cubed over 12. Uh, Base is 1, height is 2 over 12. So that's in meters. We will have a unit of meter raised to 4. So 2 raised to 3 over 12. That's 1. You can neglect that. That's 0.667 meter raised to 4. Or we can also use the fraction form. That is 2/3. Okay? 2/3 meter raised to 4. So the area is 1 times 2. That's 2 meters squared. Okay, we can now locate the horizontal force. Bar Y is 6 meters plus IG. So that's 2/3 meter raised to 4 over area, that's 2 square meter times bar Y 6 meters. So let's directly compute this. 6 plus 2/3 of over 2 times 6. Okay. So this is your answer. 6.05. That's 6.05 meters. Okay. Okay, or 6.056 meters. Okay. Okay, we're done with horizontal force. We come now to vertical, FV or Fy. So for the vertical force, again, the vertical force is just the product of the unit weight of the fluid and the volume above the curved surface. So again, if we will extend the edges of this curved surface right here, okay, the volume covered by this up to the water surface is your volume required. So since here we are required to determine the location uh, of this vertical force, so since the shape form is an irregular shape, or it consists of a quarter circle and a rectangle, so we solved separately the vertical force due to this rectangular prism form right here, because we have a width, as well as we solve the vertical force due to this quarter circle. Okay, so we have two forces, two vertical forces right here. The force due to this rectangular shape volume of water, and this quarter circle, because later on when we will determine the centroid, or the location of the sum of these forces, so um, we will apply Varignu's theorem. So we cannot solve that without solving this separately. Okay, so let's say this rectangular shape equivalent vertical force is Fv, and this for this quarter circle is this W. So it means our Fy is the sum of W and Fv. Okay, so that uh, W first, the weight or the equivalent vertical force of the quarter circle. So the volume for the quarter circle is just equals to one-fourth of the area of the one-fourth of the area of a circle, and we will multiply that to the width, which is 1 meter, so that we can determine the volume. So 9.81 kilonewtons per cubic meter multiplied by the area first of this quarter circle. So one-fourth of area of a circle, pi r squared. So r is 2 meters. So square multiplied by the width, or this 1 meter. Oh, that's W. So 9.81 times one-fourth is 0.25 times pi times 2 squared times 1. So the answer is 30.819. 30.819 kilonewtons. Next, for Fv, for the volume rectangular of this rectangular shape right here. So multiply again unit weight of the fluid times the volume. So just determine the area and multiply to the width, which is 1 meter, width of the gate. Okay, so it's 9.81 kilonewtons per cubic meter multiplied by the area of this rectangle, 2 by 5. It's 2 by 5. 2 meter by 5 meter times the thickness 1 meter. So the vertical force is 9.81 times 2 times 5 times 1. 98.1 kilonewtons. So the total vertical force, say Fy, is equals to W plus Fv. So 30.819 kilonewtons plus 98.1 kilonewtons. That is equals to 128.919 kilonewtons. So this is the answer. For the resultant force that is equals to square root of f of x plus f of y. So square root of the horizontal force 117.72 kilonewtons, raise that to 2, plus Fy 128.919 kilonewtons square. Okay. So square root of 117.72 square plus 128.919 square. 174.58 kilonewtons. So means this is your equivalent force acting on this curved surface right here. Okay. So for the location of these forces, f of x, we have already determined the location of the horizontal force. How about the vertical force? So for the vertical force, let's determine the location of Fy. So to find the location of this total vertical force Fy, we will use Varignon's theorem. So if the distance required to locate the, the total force Fy is bar x, so we will just multiply that to Fy and we will equate that to the sum of the products of the two forces Fv and its equivalent distance, as well as W with its distance. So the sum of the products of the force and its distance. So Fv times x1 plus W times x2. So what is x1? Since this is just rectangle, so our location for Fv is at the center of gravity, and for the rectangle, the center of gravity is at the middle. So if we will just locate its position, its location horizontally, so just take the half of this 2 meters distance. So half of 2 meters, x1 is 1 meter. So Fy bar x, Fv, that's 1 meter. That's W, x2. How about x2? So for x2, the distance from this side to W, or the location of that force or the centroid of this quarter circle, so we have a solution for that. That is, we have the x2, which is equals to 4r over 3 pi. Okay, so let's review the given. We have Fy, Fv, W, and radius. So let's substitute all that. We have an Fy of 128.919 kilonewtons times bar x equals to Fv. Our Fv is 98.1 kilonewtons times 1. W is 30.819 kilonewtons times this solution right here. That is 4 times R. R is 2 meters. So 2 meters, 4R over 3 pi. So let's compute first each term. Okay, this will remain 128.919 kilonewtons bar x equals to 98.1 kilonewton meter plus 30.819 times 4r over 3 pi. So that's 26.221 kilonewton meter. So 128.919 kilonewtons bar x plus just add 98.1, that's 124.321 kilonewton meter. Divide both sides by 128.918 kilonewtons. We have an answer for bar x that is equals to 0.964. Okay, 0.964 meters. So your bar x is 0.964 meters from this side. So that's the location of your vertical force. Okay. So for the line of action of the hydrostatic force, we can also solve that by determining the angle. Okay, by determining the angle formed by the vertical force and the horizontal force. So the line of action, let's say we have located now the force, the resultant force. Let's say this is your quarter circle, this is your Fy, this is your f of h. So we already located this using yp, and this distance right here is your bar x. Okay, the line of action can be computed, which is this will be your resultant force. So you can compute that by forming a force triangle. So if we will redraw that, this is f of x, f of y is downward, this is your resultant force, this is your theta right here. So the line of action or the angle of that force is this theta right here. So applying trigonometric function tangent theta, that is equals to Fy over Fx. So theta is equals to arctangent of Fy over f of x. So computing that, we have f of y, which is 128.919 kilonewtons to be divided by f of x. F of x is this one, 117.72 kilonewtons. So theta is arctangent 128.918 over 117.72. 47 degrees. Okay, it's 47.5996 degrees. So that's the answer. Okay, so that's how you solve hydrostatic force on curved surface. So let's try another example. A sluice gate is in the form of a circular arc of radius 6 meters as shown. Let's compute the horizontal force, vertical force, and the magnitude of the resultant force acting on the gate. So letter A first. The horizontal force. So we already have the cross section on the side elevation of this curved gate right here. So we form a rectangular surface which is 2 meter by 4 meter. So applying the solution, f of x or f of h equals to gamma bar h a. So since one edge of the rectangle is on the water surface, so we can easily determine bar h, which is 2 meters. So f of x is 9.81 kilonewtons per cubic meters. Say this is water. Okay, multiplied by bar h, 2 meters, and the area 2 by 4. 2 meter by 4 meters. So this is your area. So f of x is equals to 9.81 9.81 by 2 by 2 by 4. 156.96 kilonewtons. That's the answer. For letter B, vertical FV or FY, say FY, uh, it's the product of unit weight of water and the volume. So the volume here, if we will extend the edges of this curved gate vertically, so if we will extend this upward, the volume form is this one. So we have a width of 2 meters. So we have an area of a quarter circle and we have a width of 2 meters. Okay. So the direction of that force, since this is not filled with water above this curved gate, it means our force is upward. Okay, the direction of our force is upward. So unit weight 9.81 kilonewtons per cubic meter multiplied by the volume. The volume is this one. Area of quarter circle, 1/4 of pi r squared. R is 4 meters squared. Multiplied by the width, 2 meters. So this is your volume. So the vertical force is 9.81 times 1/4.25 times pi times 4 square times 2. That's 246.552 kilonewtons. So that's the answer. For letter C, magnitude of the resultant force acting on the gate. Okay, force equals to the square root of fx squared plus fy squared. So just take the square root of squares of 156.96 kilonewtons squared plus 246.552 kilonewton raised to 2. So F is equals to square root of 156.96 square plus 246.552 square. The resultant force is 292.274 kilonewtons. So these are the answers. Okay, so we have a horizontal force and vertical force. So that's how you solve it. Last problem. A sluice gate is in the form of a circular arc of radius 6 meters, as shown in the figure. Compute the horizontal force acting on the gate, the vertical force, and the magnitude of the resultant force. Okay, first let's compute the horizontal force, Fh or Fx. So to compute the horizontal force, we have gamma bar H times A. So if this is water, we have 9.81 kilonewtons per cubic meter multiplied by bar H. Bar H, since the gate has its top portion in line with the water surface, so our bar H is just one half of the vertical distance of this sluice gate, which is 2.5. So we have a rectangle, one half of that, of the height is 2.5. So 2.5 meters for bar H, and for the area, length times width, 1 by 5. So let's compute now the horizontal force, 2.5 by 5, 122.625 kilonewtons. Okay, letter B. Compute the vertical force acting on the gate. So again, uh, this is your sluice gate, curved surface. Again, you will extend both ends of the gate upward up to the water surface. So our ends is here and here. So top and bottom. So if we will extend that up to the water surface, so this point right here is already at the water surface. So we need not to extend that upward. But here at the bottom portion of this sluice gate, extending that upward, okay, the area or the volume covered by the sluice gate and this line here is your volume required to determine the Fy or the vertical force. So this is just a segment of a circle. So we have a given radius of 5 meters and we have a central angle of a total of 60 degrees. Okay, that's a total of 60 degrees plus 30 degrees on each side. So if this is segment of a circle, we have to determine the area first, then we multiply the width so that we will be able to determine the volume. So general solution for the vertical force is unit weight times the volume. So the volume, we must find first the area, then we multiply it by the width, which is 1 meter. So the area. So for the area of the segment, we can solve that by determining first the area of this sector formed and subtracting the triangle that is also formed by the sector. Okay, so this triangle here, we subtract that to the area of the sector. What remains is the area of the segment. So for the area of a sector, we have solution of pi r squared, then multiply it by the ratio of its central angle to the total angle of a circle, which is 360 degrees. So the central angle is 60 degrees divided by 360 degrees to be subtracted by the area of a triangle. We can, since we have a radius, this is also the radius of 5 meters, so we have two sides and an included angle of 60 degrees. We can apply 1/2 AB sine theta or 1/2 r squared sine theta or the included angle, which is 60 degrees. So substitute r, 5 meters square times 60 over 360 degrees minus 1/2 5 meters square sine 60 degrees. Okay, so we can solve that. Now, the area of the segment is equals to pi 5 square times 60 over 360. Then add area of the triangle. So subtract area of triangle 1/2 5 square sine 60. So the area of the segment is 2.265 square meter. So the volume of the segment, okay, the volume when we multiply the width is 2.265 meters square multiplied by 1. Okay, that's 2.265 cubic meters. So we can now compute the vertical. 9.81 kilonewtons per cubic meter times volume 2.265 cubic meters. So Fy is 9.81 times 2.265, 22.21965, 22 kilonewtons. So for the resultant force, we have F equals to square root of Fx squared plus Fy squared. So square root of 122.625 kilonewton raised to 2 plus 22.22 kilonewton raised to 2. So F is equals to square root of 122.625 square plus 22.22 square. That's 124.622. 124.622 kilonewtons. That's the answer. Okay. So that ends our lecture for hydrostatic force on plane and curved surface. Thank you for watching. God bless.